Hello, class. I would like to finish chapter 5 lecture. We are having, let me see, go back here. Oh, chapter 5 lectures. I would like to start looking at the summary of chapter 5 because this all the amenity that you needed. So first, you're looking at 5.1, basics identities. So this identity we have talked in, I think in chapter in the past. I don't remember exactly the chapter, but I told you to like copy this down, right? Or take a quick picture or something to save it somewhere. Or you can print this out. You can print this out so that when you do the work, you can, like if you cannot memorize this formula, you can check back with this one. So we do have the basic identity for reciprocal. Reciprocal including the following. So I count 1, 2, 3, 4, 5, 6. So total 6 of the SIG formula for reciprocal, SIG identity for reciprocal. And we are having cosecant theta equal to 1 over sine theta, right? So this is you usually using this more than I think we're using all of the reciprocal formula mostly. Mostly you might see cosecant, secant, sine, cosine, tangent, and cotangent is rare. So this you should write it somewhere. And we have the ratio. Ratio we only have two. We have tangent theta will be equal to sine theta divided by cosine theta, and cotangent would be the opposite, which is cosine theta divided by sine theta. Let me see and make sure I'm recording. Okay. Pythagorean theorems. You have heard this Pythagorean. You have heard this Pythagorean theorem. Keyword to apply the right triangle, right? So right now, actually, this consider a right triangle as well. So when we're drawing the unit circle, you are having, when you draw the angle that in the right triangle in the unit circle, you will notice that cosine square and sine square add together will give us 1 by using a Pythagorean theorem. Actually, so this Pythagorean theorem you can apply for this formula, okay? This formula right here for trig. So the basics, the formula that you're using a lot for proving, for solving, will be cosine squared theta plus sine squared theta equal to 1. Okay, and this is also the formula for a unit circle as well. And the second formula will be 1 plus tangent square will be equal to secant squared theta. Okay, sometimes you're using this, sometimes you're using 1 plus cotangent square equal to cosecant squared theta, but you're using more on 1 plus tangent squared theta equal to secant squared theta. And the next formula would be sine squared theta would be equal to 1 minus cosine theta because of why? They're using this. Okay, so to find sine squared theta, you minus cosine squared for both sides. So you got this formula. And from there, you keep solving for example, for solving for sine theta, you will square root both sides. You square root both sides. And then the answer will be sine theta will be plus and minus square root of 1 minus cosine square. Okay, theta. And over here, they have, I think they did something, the small mistakes right there, minus theta right there should be theta or parentheses. Okay. Right, so square root of that, yeah, that's right. And cosine squared theta, so it will be the other opposite. So they're using cosine squared theta plus sine squared theta equal to 1. To find cosine squared theta, you minus sine squared theta for both sides, then you would have 1 minus sine squared theta, okay? So, and to find cosine theta, you square root both sides as same as sine theta. You square root both sides, you got plus and minus square root of 1 minus sine squared theta. Right, so they make mistakes right there. All right, so Pythagorean theorems would be three main formula, and the sub equation, sub identities will be, you just do the basics math and you got the answer. So for proving identity, like I said, you need this table. You need this basics identity table to help you proving, because almost of the time you convert secant, cosecant, cotangent, tangent, stuff like this. So you will convert all of this into the simple form, which is the fraction like this. And then from there, you will prove slowly and got the answer. So when you're proving something all the time, you will need this. You will want to convert um, the general form into the smallest form. To me, like smallest form, involving sine and cosine. Okay, so for even here, one cotangent theta equal to 1 divided by tangent theta. So you should convert this more. So tangent will be equal to sine divided by cosine. So cotangent will become cosine theta divided by sine theta. So make this small, simple form like this before you proving. So to proving all the time, you're looking at, for example, over here on the left side, they want us to prove tangent x plus cosine x equal to sine x times secant x plus cotangent x. So this is very, so you know you got two sides, right? The right hand side and the left hand side. The left hand side is tangent x plus cosine x, and the right hand side is sine x times secant x plus cotangent x. Compared to these two sides, you would asking yourself like which side would be more complex. So we always start from the complex side, and then make the complex side become simple size. So in this case, the right side will become complex side. So we're going to start from here. We're going to start from sine x times secant x plus cotangent x. We start from there. We break these terms like secant and cotangent down, and then using algebra, and then do it, or you can distribute it and then break it down, then reduced. You can do that way as well. So in the textbook, they teach us like, okay, so they want us to start the right hand side. Yes, you can start from that. Of course, you can start from your left hand side, but if you start from your left hand side, which is a simple form sign, simple form, it's not like easier. It's not help you kind of break down and figure out that tangent x plus cosine x will become this complex term. It's difficult because you need to break out more, like pull out more, express, like expand more than the right term. The right term, you when you start, you will condense, make it like you simplify it easier. So what we're going to do, we're going to distribute sine x with secant x, right? So we have this term, sine x times secant x plus sine x plus cotangent x, okay? So you got now, it's become two terms now, two big terms. So now you're going to start at, break down secant x into 1 divided by cosine x, okay? So put all the time is equal sign because this term equal to that term. But that doesn't mean this right term equal to your left side yet. Is you're not allowed to writing down the whole thing and then break it down, right? Because we are proving. When you're proving, it means you start from one side and make that one side become the other side. And then you say, okay, I have proved this two equal. Then you're done. Okay, so if you're confusing, you should start exactly like the textbook, or you want to tell me like, okay, I start from my right hand side equal to this term, this big term, and then I break it down. And then this equal, at the end is equal to tangent x plus cos x. That is my left hand side. Okay, like that. Then it's proving. So let's continue. So now you break sine x times cotangent x will become plus. You just drop it down. You rewrite this. Got cosine x divided by sine x. So from here, now this become one term, and this is another terms. So what you need to do, you got sine x times 1 is sine x divided by cosine x. So this is the formula above here, right? Sine x ratio. Sine x divided by cosine x is our tangent x, right? So this case is theta. So right as the proving problem is x, so you write x. So this becomes tangent x. That's for first term. Plus, drop it down to plus. How about this second terms? You got sine x as the numerator, divide the denominator. Cancel out. You got cosine x divide 1 as considered as one term. So this becomes cosine x. So now from the right hand side, you simplify, you make this become tangent x plus cosine x. That is our left hand side. Then that's how they showing is proving. Sometimes they want us to prove, but you cannot prove it, right? You cannot prove. There's some case that we cannot prove it. Then you say, okay, this is not equal. So, but if they want you, but mostly like 95% all the time when they want us to prove something, all the time the left hand side will be equal to the right hand side. But we have to check the process where you start and how you simplify by using the basics identities. So that is one of the form the example for proving about the topic sum and difference formulas of in 5.2. So this even though we're not using this a lot on our work in our work, however, you should know this formula. Sometime you will see this type. Okay, so this type helping you to break down and simplify from the big angle become the smaller angle. So the formula, we are having the sum and the difference is as below. If you got sine of a plus b, okay, so this will become sine A times sine B, time cosine B, time cosine B, plus cosine A times sine B, and so on. You can read this by yourself too. So be careful with the angle, right? Be careful with the angle and following the sign. So this, for me, myself, I don't remember of this. So I copy down somewhere so that I can look at it because, um, it's because we don't apply this a lot. So that's why I don't remember it. Actually, you only need to understand this formula like this. Every time you see like the angle, add with another angle, you have this formula. It's expanded out and so on. Even so, for example, the cosine of a plus b will be equal to cosine a times cosine b minus sine a times sine b. Okay, so and so on for tangent as well. And we do, of course, we do have some exercise related to this, but it's not common. It's not like formula. It's like popular. However, like I said, you should know this. Okay, you don't have to memorize this, but you should know it. And the example for doing this will be the left side. To find the exact value for cosine 75 degree, we write 75 degree as 45 degree and 30 degree because 45 degree and 30 degree, they are special angle, right? So when you break it down like this, you are allowed to break it down like this. That is helping you to find the exact value easier because in actually for cosine 75, of course you can use calculator, right? It's just like, okay, press calculator, you got a value right away. However, in this process, it's not the purpose is like you using calculator. The purpose like you need to apply the formula to expand it and show it. That is the purpose. But if I say like if I write a test and I write like use whatever method that you want, you can apply the calculator. Just press in cosine 75 degree equal to a value. You can do that. But if like I want you to find by apply the formula, not by apply the formula, you must write the formula. But if you don't follow directions, you got like about 70% taken up, because every time that you solve something, for my grading method, my way of grading your work is seven. My rubric, my seven will be 70% of that you show your work, and another 30% will be the solution. So I'll let you know my rubric later when the midterm is come. But all the time like this, I all the time want you to show your work in details carefully so that I can see the steps. And then of course, the solution, you box it, you box your solution. Okay, so like you looking at this example, you got cosine 75 degree equal to cosine of 45 degree plus 30 degree. Because of cosine related right here, so we use using this formula. So you have cosine of 45 times cosine 30 degree minus sine 45 times sine of 30. And then from here, you using the table that I show you, the table. If you cannot remember um the value for cosine 45 and cosine 30, you check back module 1. I have the table for you to look at. But for this special angle, I recommend you should memorize it. Just memorize uh, cosine 30, cosine 0, cosine 45, cosine 90, and sine as well. From there, easier to do, you do work quicker. Okay. Otherwise, you have to look at the table. But because it's online class, so I don't mind. But if it's face to face, many instructors require you to memorize the table, the special table, so that you can do quicker when it's on the test. Okay, so we're using algebra. You are having square root 2 times square root 3 give you square root of 6. And 2 times 2 give you a 4 minus. The reason they combine this because they have the same denominator, so they combine as 1. So then this minus here will be dropped out here. So square root of 2 times 1 is square root of 2. And you got square root of 6 minus square root of 2 divided by 4. So let's be using calculator to figure it out. If you're using the calculator, what happened? Okay, let me see. So you can use TI 84, 83, 89, or you can use your iPhone. I'm using my iPhone right now to check. You got square root of 6, so I'm going to type in number 6 and then square root that. Okay, minus square root of 2, so I remember square root of 6 is 2.45. Okay, 2.45. And square root of 2 is 1.41. So I would take that. 2.45 minus the square root of 2 is 1.41. I have 1.0357. So let's write it up to 1.04. So I have 1.04. I divided by 4. I have the value is 0.26. Okay, I got a value 0.26. So let me check if cosine 75 degree. So you got 0.26 in radian. And I'm having cosine 75 degree. I'm sorry, that in degree, 0.26 is in degree. So when I take my calculator, I'm having, I type in 75 and then I click cosine and then they give me the value. But remember in degree mode, okay? because I'm using in degree mode at first. So at this time I'm using in degree mode as well. So my value, when I type in like that, I have 0.2588. I rounded up, will become 0.26. So doing calculator is quicker. However, the purpose is not like for this section, it's not like just find a value, but they want you to practice the formula. That is one of the example. Maybe on the homework they require you to using um, uh, the maybe you break it down and figure out a value, because they might just like give you like the missing part, and you're the one who put in for example, you put in cosine of 30 degree, right? They write the whole thing for you, but they you know, they just erase some terms, and you the one have to plug it in by using this formula. Okay, so double angle formulas. Double angle formula we have, we're focusing to, which is side 2a. Like we're using a lot side 2a, and we're using a lot cosine 2a, but side 2a is more common. So side 2a equal to 2, number 2, time sine a time cosine a. Okay, so for cosine 2a, you got 3 formula. You got cosine square a minus sine square a. And you got another formula is 2 times cosine square a minus 1. Another formula is 1 minus 2 sine square a. So these 3 formula or 3 forms helping you to figure out cosine 2a. So the reason they having this is because sometimes they given you, you know, cosine and sine, they want you to find cosine 2a, then you will use the first form. For the formula, for example, on the left side right here, they give you only sine a. So the only formula that you can use is 1 minus 2 sine square a, right? Apply for this. And you got cosine 2a will be equal to 7 divided by 25. Half angle formula. Half angle formula, we are having sine of a divided by 2. So, okay. So that would be equal to plus and minus square root of 1 minus cosine a divided by 2. Cosine of a divided by 2 will be equal to plus and minus square root of 1 plus cosine a divided by 2. Okay, I think the best way is you print it out, because too many formula, right? Too many formula in one chapter. So I think you should you don't have to write down a piece of paper. You can print it out. But if you have more time so that you want to remember it, write as many time on your notes. Number 4 is the example for half angle formula. Half angle formula, you will see like something divided by 2 like this. So they given us like, if cosine theta is 1/2, they give us cosine theta is 1/2, not cosine of theta divided by 2. So if they give us like this, and theta is between 0 to 90 degrees, which is in the first quadrant, you'll notice in the first quadrant, cosine will be positive, right? So when you're writing it, you don't have to including the negative sign for cosine. Okay, so you're thinking like, okay, my theta is that. So now my formula for cosine of theta divided by 2, I'm going to have square root of, I take a positive square root of 1, which is this one fixed, minus cosine A. So for this here, cosine A or cosine theta, you got given is 1/2. You can plug it in. Divided by 2, 2 is fixed. So then you simplify this. Before you simplify this, you have to do the algebra, 1 plus 1/2. This give you 3/2, right? If this will give you 3/2 divided by 2, you using reciprocal of divisions, and you have 3/4. If you forget this, let me annotate, because I think some of you might forget this one. So 1 plus 1/2, right? So this, because the denominator is 2, so you make this become 2/2, because 2/2 is 1 plus 1/2. This gives you 3/2. And now you do a side work, so you don't need to do the math in there. You can do a math outside on a scratch, and then you write that value on the top. So now on the top we become 3 divided by 2. The bottom is still like this. So this now become 3 over 2 times 1 over 1 half, right? Because 2 over 1 become this division, become multiplication. You flip it over, you got 3, 4. So 3, 4 becomes square root 3 divided by 2, right? Because square root of 4 is 2. So all of this basic algebra you must know before you take the class. So I hope that it's a quick review for you. So now the answer is square root 3 divided by 2. Let me erase this. Okay, so section 5.5, products to sum formulas. You already have products, you expand this product into the sum formula, right? Like this. It's a long formula, but it's nice that you know, for trig here you cannot like sometimes they expect you to apply formula to like expand them out and everything. um but if sometimes I'm saying if sometimes it's obvious, like the value like side of 30 degree time cosine of 30 degree or 45 degrees, something like that, you can multiply them together directly. You don't have to use formula, but using formula is sometimes it's happen like this. Okay, so like the example number 5 right here. So we can write the products 10 times cosine 5x times sine 3x as a difference by applying the second products to some formula. So they're having this. So the reason is, so the reason they're doing this because, again, like I said, they want you to practice all the trig formulas. Okay, but right in this case, is x is unknown. So the best way to do it to know to simplify this is that. Okay, so for number 10, in front of that products here, you just pull it out. You know, when you is multiplying, you pull it out everywhere in the front. And then by using that formula, you got 1/2, right? 1/2 times the formula thing. And then from here, you will, you know, you can distribute it, or you using what formula. So let's say right here, 10 times 1/2 give us a 5. That's 5 right here. And side of 5x plus 3x, because 5x and 3x are like term. Because it's like term, you are allowed to add. But if it's not like term, you cannot add. Okay, so let's go back to a bit up here. Let's see, I noticed that, for example, like this, 45 degree and 30 degree, they like term. However, we cannot just add them because our purpose is finding cosine of 75 by using this, you know, sum and difference formula. So that's why you don't, you know, like just add and got a value. Over here, x term right involving right here telling us your x is unknown. So you add like term, you got 5x plus 3x is 8x, and minus sine of 5x minus 3x, like term again, you can subtract, and you got this value. Okay, so right here they stop. Sometimes they want you to expand it more, but I think it's not necessary. If you expand it more, you got sine 2a, right? Sine 2a equal to 2 times sine a times cosine a, right? But you should not expand more. This is you simplify and then I think that's good enough. Okay, sum to products formula. So this formula, okay, again, right here, you should know, even though it's rare. So, and having this, we are having the example applied to this is you can prove something. So right here is we're proving minus tangent x equal to cosine 3x minus cosine x divided by sine of 3x plus sine x. See that? It's kind of complicated, right? So look like the right hand side right here, you notice the left hand side is only minus tangent x. If you're using reciprocal minus tangent equal to sine divided by cosine will be minus sine divided by cosine, and that's it, right? So it's not helping you to make that become the right hand side. So in order to prove this, you start from the complex term, right, which is here. By using the formula, and the formula that they're using is the sum to products formula for this one. So they're using this, they write it down, they're starting that, and they're using the formula on the side. In this case, as you notice, they have cosine 3x minus cosine x, right? So they have cosine 3x minus cosine x, which is they're using the fourth form. They're using this. And then apply here. It's complicated, and then they simplify. Simplify, they got this, and they got that. Oh, right, but again, on the test, I won't give you something like this. I'll give you something more like obvious, like more common use. So here will be the okay, the maybe this similar to your homework. I think that's all for chapter 5. So now we wanna, watch the lecture together with the given videos. We have, let me see. We have this. Chapter 5. Now let's do this. Let's watching this together. And again,
in this section, we're going to prove some.
On your lecture, you should try to understand this example. Okay, copy it down as the lecture for you. So now listen to the instructor.
Identities, and to do these problems, you need to have memorized those basic identities, the reciprocal, ratio, and Pythagorean identities. And then we're going to put those identities together with a little bit of algebra and prove some more difficult identities. Here's our first one. We want to prove that cosine theta times tangent theta is equal to sine theta. So I'll start with the more complicated side, and I'm going to take cosine theta, tangent theta, and rewrite it as cosine theta times sine theta over cosine theta using my using my ratio identity that says tangent theta is always sine theta over cosine theta. Now I'll divide out the common factor cosine theta, and that simplifies into sine theta. So I've succeeded in taking this expression and with a little bit of identities from trigonometry and a little bit of algebra here, simplifying it into sine theta. So I've proved that cosine theta times tangent theta is always equal to sine theta. Here's our next one. I want to show that cosine x times cosecant x plus tangent x is equal to cotangent x plus sine x. So I think I'll start on this side, on the more complicated side here, and I'm going to apply my distributive property and multiply cosine x times both of these terms here. So when I do that, I'll have cosine x times cosecant x plus cosine x times tangent x. And let's see, I have cosine x times cosecant is 1 over sine x. So I can use that reciprocal identity. And then I'll have cosine x here times, I'm going to change this to sines and cosines using my ratio identity that tangent x is sine x over cosine x. Now I'm keeping an eye on this side. I want to change this side into this side. So I'm going to need a sine x and a cotangent x. I think I've got it here. Cosine x times 1 over sine x is cosine x over sine x plus, that's my plus sign here, cosine x times sine over cosine. I'll divide out that common factor of cosine and I have left sine x. And so I see I've succeeded in getting what I want here. Cosine x over sine x using my ratio identity, that's cotangent x plus sine x. And I've succeeded in changing the left side of this expression of this identity into the right side. So I've essentially proved this identity. So you can see by watching what I've done right here that you need to know those basic identities, reciprocal identities, ratio identities, and Pythagorean identities to be able to do these problems. Here's another one. I have cosine to the fourth t minus sine to the fourth t over sine squared t is equal to cotangent squared t minus 1. So I'm going to start with this side here, and I'm going to start by factoring the difference of two squares here, since fourth powers are also squares. And so when I do that, I'll get cosine squared t plus sine squared t times cosine squared t minus sine squared t. And that's all divided by sine squared t. Now,
for this example, you need to notice the cosine to the 4t minus sine to the 4t because you see that all of the basic term, they are square. Like the bottom denominator is sine squared t, and the right side is cotangent square t. So right here they try to break down by using the formula that I showed you before, which is x squared plus or minus y squared, right, will be equal to x plus y times x minus y. This is just the same thing. You imagine they break it down cosine squared t plus sine squared t, right? They got two terms, cosine represent for x, sine represent for y, and you square it, right, and multiply it by cosine squared t minus sine squared t. So that's what they're using we call the square difference of differences of the square formula, and divided by sine squared t. From here, then later you will see you should not distribute back because you already break down from here to here. So you're not going to distribute back for each term. Or if you have to, then if we have to, then you can cancel some term is possible, but it's look like if you distribute back and then you have to combine like term, which is the numerator on the top, then starting break it down. Let's see what the instructor do.
Look and see here, I have cosine squared t plus sine squared t, and I know that that is simply equal to 1. So I have 1 times cosine squared t minus sine squared t. So this is going to be equal to cosine squared t minus sine squared t all over sine squared t, using my Pythagorean identity that says that this is 1, so 1 times this is just it itself. Now let's say I look over here, I want cotangent squared minus 1. Well, if I take this sine squared that divides this numerator and divide each term in the numerator by it, I'll have what I'm looking for. Cosine squared t over sine squared t minus sine squared t over sine squared t. And look what I've got here. Cosine squared t over sine squared t, that is cotangent squared t, minus sine squared t over sine squared t is 1. So I've done the same thing here. I've succeeded in changing this side into this side using just trigonometric identities and a little bit of algebra. So I've proved this identity.
So this means we have to apply the table, the first table, the basic identity all the time, improving and stuff, right? So let's look at 5.2.
In this section, we look at the sum and difference formulas for sine, cosine, and tangent. Here's our first problem. We want to find the exact value of the sine of 15 degrees. Now, to do this problem, I need to write 15 degrees in terms of two angles that I know exact values for. So I'm going to say that sine 15 degrees is the same as the sine of 45 degrees minus 30 degrees. So 15 is 45 minus 30, and I can find the sine of the difference of two angles by using my formula, my expansion formula, which says that this is equal to sine 45 cosine 30 minus cosine 45 sine 30. So I've memorized that formula for the expansion of the sine of A minus B. Sine A cosine B minus cosine A sine B. Now the rest is simply a matter of just substituting in the exact values I have memorized for these. Sine of 45 degrees, I'll use this exact value, square root 2 over 2. Cosine of 30 degrees is 1/2, minus, that's my subtraction sign, cosine 45, square root 2 over 2. And then sine 30 is going to be 1/2, and let's see, I made a mistake, right? Cosine of 30 is not 1/2, it's square root 3 over 2. Cameraman found that mistake, okay. Square root 2 times square root 3, square root 6, minus square root 2 times 1, square root 2, all divided by 4. Now, that's kind of a complicated looking expression, but that is the exact value of the sine of 15 degrees. If you put sine 15 in your calculator and get a decimal approximation to it, and then simplify this on your calculator, you'll see the decimal approximations are exactly the same. The key to working a problem like this is that you have memorized this expansion formula for the sine of a minus b, and of course you have memorized these exact values. Cosine 30 is square root 3 over 2, not the 1/2 that I said the first time. Let's look at another one. We want to prove that sine of 90 degrees plus theta is equal to cosine theta. So I'm going to use my expansion formula on this expression. So I'll write sine of 90 degrees plus theta is equal to sine 90 cosine theta plus cosine 90 sine theta. And I write this out because I've memorized the expansion formula for the sine of a plus b. Sine a cosine b plus cosine a sine b. Now, I need to write down the sine of 90 and the cosine of 90. I can do a quick little picture right here. I do this a lot when I'm working these problems. I know that y equals sine x looks like this, and it's 1 at 90 degrees. So the sine of 90 is 1 times cosine theta, plus I want cosine of 90, so again, I'll just draw a little diagram right here. One complete cycle of cosine looks like this. That's 360, that's 180, that's 90 right there, so cosine is 0. So 0 times sine theta, and then I have 1 times cosine is cosine theta, plus 0 times sine theta is 0. So I've succeeded in showing that sine of 90 degrees plus theta is equal to the cosine of theta. And I proved this using my expansion formula for the sine of a plus b, and then I just substituted in some exact values for sine 90 and cosine 90. And I like to draw these little pictures of one complete cycle of sine and cosine to get some of these exact values. Here's our next problem. We want to graph one cycle, how about graph one cycle of y equal 2 sine x cosine pi over 3 minus cosine x sine pi over 3. So this time I'm going to use my expansion formula in the opposite direction to write this as y equals 2 sine of, let me get this right, 2 sine of x minus pi over 3, because I recognize this as the expanded form of sine of x minus pi over 3. Now I'll check out the coefficients that I have right here in the constant term. I have an amplitude for this graph of 2. I have a period of 2 pi divided by that coefficient, which is 1, so that's just 2 pi. And I have a phase shift of minus negative pi over 3 divided by 1, so that's just positive pi over 3. So this is where my graph will start. At pi over 3, it will end at pi over 3 plus 1 period, which is 2 pi. So pi over 3 plus 2 pi, let's say I have pi over 3 plus 6 pi over 3, that will be 7 pi over 3. Okay, so if I've got this marked off here, if that was pi over 3, that would be 1 pi over 3, 2, 3, 4, 5, 6, 7 pi over 3. So that will work. So let's label that 7 pi over 3. That's pi over 3. So I have 1 pi over 3, 2 pi over 3, 3 pi over 3, which is pi, 4 pi over 3, 5 pi over 3, 6 pi over 3, which is 2 pi, and then 7 pi over 3. So let's see, it's a sine curve. It has an amplitude of 2, so let me make that 2 and that negative 2. On the x-axis, we'll start here at 0, And let's see, it will go 1, 2, 3, 4, 5, 6. It'll be 0 in the middle, and it will be 0 at the end. Halfway in between, it will be up to 2. Halfway in between here, it will be down to -2. And let's see if I can sketch one complete cycle of this real nicely. There we go. So there's one complete cycle of y equal 2 sine x minus pi over 3, which is the compact form of this expression right here. So I've used my expansion formula in the other direction. Given the expanded form right here, I compact it down to this expression. Let's try one more problem. We want to let sine A equal 3/5 with A in quadrant 1. Sine B, a different angle, is -5/13 and B is in quadrant 3. And I want to find the sine of A plus B. Well, I know that the sine of A plus B is going to be the sine of A, the cosine of B, plus the cosine of A times the sine of B. So I have, let's see, the sine of A, I can fill that in. That's going to be just 3/5 times cosine of B, I don't have that, plus cosine of A, I don't have that, but I do have the sine of B, which will be -5/13. So I need this expression, cosine A, and this expression, cosine B. So I'm going to use this information along with the quadrant to find those expressions. So let's see, up here I'm going to draw a little right triangle. I'm going to label this angle as A, and I'm going to label the triangle so it has a sine of 3/5. 3/5, and here's my right angle. So the opposite side is 3 and the hypotenuse is 5. Now, by the Pythagorean theorem, I know that that has to be 4, which tells me that the cosine of angle A is 4/5. So the cosine of angle A is 4/5. I'm going to fill this in right here, 4/5. Now let's do the same thing with B, and this diagram is just giving me the numerical value. So for B, let me draw a little right triangle. That's the right angle. There's B. I'm not going to worry about the negative sign because I know what my cosine of B is going to be negative because B terminates in quadrant 3. Let's just take care of the numerical value. The sine of B is 5/13, meaning that's 5 and that's 13. By the Pythagorean theorem, then, I know that that's 12. That tells me that cosine of B has a numerical value of 12/13. And since B terminates in quadrant 3, I'm going to make this a -12/13. So now I can fill in this part of the problem, -12/13. Okay, I'm not going to go any farther than that with this problem. You can do the rest of the arithmetic right here. It's really pretty simple from here on. But a nice problem where we get to review some of our right triangle trigonometry and at the same time use that in one of our expansion formulas for the sine of A plus B.
Thank you. So I think that is very helpful. 5.3.
Double angle formulas. Formulas for the sine of 2x, cosine 2x, tangent and cotangent 2x. Let's take a look at our first problem. If the cosine of x is 1 over square root 10 and x belongs to quadrant 4, can we find the sine of 2x? Now you know you've memorized the formula here for the sine of 2x, and we have this. Sine 2x is equal to 2 sine x cosine x. So I know I can fill this in as 2 times, well, I don't have the sine of x, but I do have the cosine of x, 1 over square root 10. So it looks like I'm going to have to find the sine of x to put in here. Let's go up here and draw a little triangle for reference. A little right triangle in here. I'll label this as angle x. It has a cosine of 1 over square root 10. So if I label the adjacent side with 1 and the hypotenuse with square root 10, then by the Pythagorean theorem, I know that this side is going to be the square root of this squared minus this squared, which is going to be the square root of 10 minus 1, which is 9. Square root of 9 is 3. So that tells me that the numerical value for sine x is 3 over square root 10. And then since x terminates in quadrant 4, I'm going to have to put a negative sign right here. So I use this little diagram right here to just get my numerical value for the sine of x, and then I use the fact that it terminates in this quadrant to get this negative sign. Now I can multiply this out. You see it's very simple. 2 times 3 is 6. Square root 10 times square root 10 is 10. I've used the negative sign, so the rest of it's pretty easy. Let's go on and look at the next problem. Now I want to graph y equal 4 minus 8 sine squared x. Let's start by factoring a 4 out of each term. What's left is 1 minus 2 sine squared x. Then I recognize this as the expanded form of cosine 2x. So I can rewrite this as 4 times this expression right here can be rewritten as cosine of 2x. So it looks like I have a graph with an amplitude of 4 in a period of 2 pi divided by 2, which is just pi. No phase shift, it's not reflected, and it's a cosine curve. So let's see if I can sketch the graph of that real quickly. So I just draw a little coordinate system here. Here's x, here's y. And let's see, I want to have an amplitude of 4, so I'll simply label this as 4 on the y-axis and this as negative 4. I want a period of pi, so let's just go out to pi. Halfway will be pi over 2. Halfway there will be pi over 4, so this must be 3 pi over 4, and I sketched the graph of a cosine curve. Starts up here at the amplitude, goes down to 0, down to negative 4, back up to 0, and then back up to 4. So a nice cosine curve. It's going to look like this. Kind of hard to draw this on these whiteboards, but it's okay. You get the idea. Nice one complete cycle there of that cosine curve, and I used my expansion formula for cosine 2x in the other direction. Here's the expanded form. I rewrote it as just cosine 2x. Identify amplitude and period. We have the graph. One more problem. Let's just verify that sine 60 is 2, sine 30, cosine 30, just so we can have one of these double angle formulas verified. So I'm going to look at this and say, okay, sine 60, see if I can get this right this time. Square root 3 over 2. That's 2 times, okay, sine 30. Let me put a question mark here because I want to see if this is true. Sine 30 is 1/2. Cosine 30, square root 3 over 2. Let's see, the 2's divide out. Have square root 3 over 2 equal to square root 3 over 2. So that does check, and I have verified that those two expressions are equal to each other, just so we can add some weight to these double angle formulas and show you that they actually do work out. Most important thing about the formulas in this section is that you have them memorized.
Yes, the 5.4 will be our last section. No worry about 5.5, okay?
We want to work now with our half angle formulas, and I've written our first problem over on the board. We want to say, let's let sine A equal 4/5 with A in quadrant 2 and find sine of A over 2, cosine of 2A. Well, sine of A over 2, this is a half angle formula. I've memorized it, and so I know it's plus or minus square root 1 minus cosine A, all divided by 2. Now for my cosine 2A, that's a double angle formula. I've memorized that. There's a couple of different ways I can write it, but let's try this one. How about cosine squared A minus sine squared A? So either of these two formulas that I use, I'm going to have to find the cosine of A. I have the sine of A, so let's find the cosine of A. Cosine of A, well, I could draw one of my little reference triangles and do it that way. Let's try an identity here this time. Plus or minus, well, I know that A terminates in quadrant 2, so cosine is going to be a negative number. 1 minus sine squared. Well, sine squared is 16/25. So that's minus square root 25/25 minus 16/25 is going to be 9/25. And just as you'd expect, this comes out 3/5. Probably knew that it was going to be that anyways. So that comes out negative 3/5. Okay, so, whoops, something dropped. That's all right. Back to my original problem here. This is going to be plus or minus square root of 1 minus cosine A, and here I have cosine A, so 1 minus negative 3/5, so 1 plus 3/5, all divided by 2. Now let's see, this is 5/5 plus 3/5, that's 8/5 divided by 2 is going to be plus or minus square root of 8/10. So that, in reduced form, is going to be plus or minus square root of 4/5. And so that is going to be plus or minus 2 over square root 5. So this is the answer, except I need to determine what sign this is going to be. So let me go back up here and say I know that A is in quadrant 2. So that means that 90 less than or equal to A less than or equal to 180. And what I'm looking for here is the sign of A over 2. So I need to know the quadrant that A over 2 is in. So I'll divide all of these by 2. And I see that I have 45 degrees less than A over 2. I'll make that less than or equal to 90 degrees. So I see that A over 2 must be in quadrant 1 if A itself is in quadrant 2. So that tells me, because of this, that I'm going to choose the positive sign right here. So my answer is going to be 2 over square root 5. It's positive 2 over square root 5. So a little messy right here maybe, but the idea is this. I have this formula memorized for a half angle formula for the sine of A over 2. Okay, so I write the formula down here. I say I need cosine. I go back up here and find the cosine of A, substitute it in, work out all the arithmetic. The last thing I do is decide, well, I need to determine what sign this is going to be, what algebraic sign. I go back and look and see that A is in quadrant 2. That means that A over 2 must be in quadrant 1. Let's try another problem. I have cosine 2A is cosine squared A minus sine squared A. So I'm going to write this as, let's see, cosine squared A. Well, I found that cosine A was negative 3/5 previously, and then sine squared A was, or sine A was 4/5. So I'm going to end up with 9/25 minus 16/25. So I should end up here with negative 7/25 for the cosine of 2A. So cosine squared A minus sine squared A, substitute in the values I have from problem number 1, get negative 7/25. So that's not too bad. Pretty easy. I think the double angle formulas are a little easier than the half angle formulas. Let's look at our last problem, which is secant 2A. I want to find the secant of 2A. Well, that shouldn't be bad because secant is 1 over cosine. So I have secant 2A is 1 over cosine 2A. I already found the cosine of 2A, so it's 1 over negative 7/25. And the reciprocal of that is going to be negative 25 over 7. So that's probably the easiest problem of the three, just using my reciprocal identity that secant 2A is 1 over cosine 2A. So that's a quick look at some half angle formulas.
Okay, class. Thank you very much. If you have any question, again, please email me or ask me in class or email in the forum so that your friend can help you. And I recommend that if you don't understand it, you can go back to ebook. Okay, read over more example for you, so that can help you understand more. Plus, let me see what else. And the table summary, yeah, table summary will help you more. Okay, and I think that's it for chapter 5. Very simple. Okay, class, I see you in chapter 6, and you have a good day.